Welcome to this video presentation on conduction heat transfer. Today we'll be analyzing example 4, which involves determining various heat transfer parameters for a furnace wall. This diagram illustrates a temperature distribution through a furnace wall composed of 3 layers: fire brick, high temperature block insulation, and a steel plate. We can see the hot gases at 810 degrees Celsius on the inside and outside air at 26 degrees Celsius. The temperatures at the interfaces are given as T1 808 degrees Celsius, T2 at 777 degrees Celsius, T3 at 78.5 degrees Celsius, and T4 at 78.4 degrees Celsius. The thicknesses of each layer are also indicated. Our task in this example is to determine several key parameters. First, we need to calculate the rate of heat per unit area of the furnace wall. Second, we'll find the thermal conductivities of the block insulation and the steel. Third, we'll determine the combined convective and radiative heat transfer coefficient for the outside surface of the furnace wall. Fourth, we'll calculate the heat exchange by radiation between the hot gases and the inside surface of the furnace wall, given the absorptivity and emissivity of the fire brick surface as 0.82. Finally, we'll determine the convective heat transfer coefficient for the inside surface of the furnace wall. Let's start by listing all the given parameters for our solution. We have the hot fluid temperature, THF at 810 degrees Celsius, the interface temperatures as earlier indicated, the thicknesses of the layers. LA for fire brick is 6.5 centimeters, LB block insulation 12 centimeters, LC steel casting is 0.65 centimeters. The thermal conductivity for the fire brick, Ka, is 1.13 watts per meter degree Celsius, and emissivity of the fire brick is 0.82. Finally, the Stefan-Boltzmann constant, sigma, is 5.67 times 10 to the power minus 8 watt per square meter Kelvin raised to the 4th power. Now let's calculate the rate of heat transfer per unit area of the surface wall, denoted as Q. For steady state heat flux in resistances in series, the heat flow Q is constant throughout all layers. We can calculate Q using the temperature difference and thermal resistance of any known layer. We'll use the fire brick layer A, for which we have all the necessary information. So Q equals the temperature difference across layer A, which is T1 minus T2 divided by the thermal resistance, LA over Ka. Substituting the values we have and calculating, we get the result as 538.9 watts per square meter. Next, we'll determine the thermal conductivities of the block insulation, Kb, and the steel, Kc. Now, since the heat flux Q is constant throughout the wall, we can use the same Q value we just calculated for the block insulation. Qb equals the temperature difference across it, T2 minus T3 divided by the thermal resistance, Lb over Kb. Rearranging to solve for Kb, this gives us a value of approximately 0.0926 watt per meter degrees Celsius. Similarly, for the steel layer, Kc equals Qc times Lc divided by T3 minus T4. Substituting the values, with yields Kc as approximately 35 watts per meter degrees Celsius. Now let's find the combined convective and radiative heat transfer coefficient on the outside surface, denoted as HO. The combined coefficient is equal to the total heat flux Q divided by the temperature difference between the outer surface, T4, and the cold fluid, TCF. And when we substitute the values and calculate, we get HO to be equal to approximately 10.28 watts per square meter degrees Celsius. Moving on to part 4, we'll calculate the heat exchange by radiation, QRAD, between the hot gases and the inside surface of the furnace wall. Now, assuming the emissivity of the hot gases as unity, the net radiation heat gain of the wall per unit area is given by the formula emissivity times sigma times the fourth difference of the fourth power of the hot fluid temperature and the inner surface temperature. So substituting the values accordingly and calculating, we get a value of 471.2 watt per square meter. Finally, for part 5, we determine the convective heat transfer coefficient for the inside surface of the furnace wall, denoted by H convect. Now, since convective and radiative heat transfers between the gases and the wall occur in parallel, the total heat flux Q is a sum of the radiative heat flux and the convective heat flux on the inside surface. Therefore, the convective heat flux on the inside is equal to the total heat flux Q minus the radiative heat flux QRAD. So substituting the values and calculating gives us 67.7 watts per square meter. Now, to find the convective heat transfer coefficient of the inside surface, we divide the convective heat flux by the temperature difference between the hot fluid and the inner surface. So 67.7 divided by 810 minus 808 yields approximately 33.85 watt per square meter degrees Celsius. This concludes our detailed solution for example 4. Thanks for watching. Like, subscribe, and share.